Okay, so here we proceed through section 4.9 now. Still talking about the chain rule. There's an issue that comes up when you're taking second derivatives, and this is an issue that you probably never noticed in single variable calculus classes. Partly for segue purposes and partly just to observe why you never noticed this in second derivative, in single variable calculus classes, I wanted to actually address the question of second derivatives in single variable calculus. Okay, so suppose you have a composition of functions, and keep in mind by this what I mean is, we've got some function f like that and g like that. And you're interested in this composition, you take a derivative and you do the chain rule. Old news. Right. By the way, here's an alternative notation. Now, for what's written above there, that's just writing the partial derivatives as with subscripts instead of as fractions. And again, that's convenient sometimes. This is going to be one of those times when subscripts are super handy. Okay. All right. So what would you do if you wanted to write a second derivative here? Well, what you'd probably do is you would have already had this written as a function of x. And you would just use the chain rule again, right? So it's seemingly seamless, streamlined, that there's nothing special that happens in with second derivatives, but not so. It's because we rewrite everything or have everything already written as a single function of x that we just don't kind of notice what I need to show you here. Okay, so let's not have everything written as a function of x. Let's leave it in this form, and now let's take our second derivative with respect to x, and let's see what happens. I'm going to zoom back in. Now, what students want to do often is say, okay, well, we're going to take an x derivative there, so I guess we should just take an x derivative over here of that side of the equation, and it's a product. We'll just use the product rule, and among other things, I guess I should leave that there. In taking the derivatives of both sides of that equation, forgive my sloppy notation. Among other things, you will get, let's see here, at some point, the derivative of zy, which students then want to rewrite as, and of course there's other stuff involved here, and I'm just skipping to the part that's relevant. Students think, okay, well, derivatives are supposed to be subscripts, so I'm going to rewrite this as z xy. And this is something I want to talk about. Can you do that? Does that make sense? And I say the answer is no. This makes no sense at all. It really doesn't. Let me expand on why this makes sense. Keep in mind this subscript business is just a shorthand for derivatives. Keep in mind that derivatives are something you can do to functions. Right? So we talk about the derivative of a variable with respect to a variable, but what we really mean is here's a function. We want to take the derivative of the function, and it's output variables and input variables, and it's notationally convenient. But we take derivatives of functions. What function is this allegedly a derivative of? Now, let me answer that question in regards to other things. What function is this a derivative of? zy. Oh, okay, well that's the derivative of that function where z is a function of y. It's the derivative of the g function. That's the name of that function whose derivative is this, g. Okay. What is this the derivative of? Well, it's the derivative of this function, f. So, cool. That's fine. If we were to claim that we could write this down, well, it suggests that z is somehow a function of both x and y. Can you do that? Is that a function, really? And no, it's not. This is not g. G is a function of y only. It's not f, which is a function of x only. It's not the composition. The composition of z is a function of x only. You can't make this a function because x and y are not independent. Y is prescribed by x. Right, so this whole thing, you can't make that a function. This is not meaningful, something to write down. The whole thing is garbage. Right, does everybody see the problem there, I hope? So anyway, this is certainly something you can't do. So what we have to do then, and again, there's circumstances, then I still want to take another derivative of, okay, so this is clearly not something we can do. We're going to have to figure out how to make sense out of what it should mean to take the derivative of zy with respect to x. And here's how I like to do it. I like to think through, well, what is this thing zy? What is zy? And where is that on my diagram? Is it in there somewhere? And I point out that, yeah, it really is, because zy, if you think about it, z was a function of y. See? Z is a function of y. If you take the derivative of a function of y with respect to y, you get another function of y. So zy is right there. We append our diagram. This is a function of that. That's where it is. Okay? Note I have this on my appended diagram right here. Zy is a function of y, just like z was. Yx is a function of x, just like y was. And on this appended diagram, when we find ourselves, as we will down here, looking at the product rule, oh, okay, this doesn't quite fit. Applying the product rule, taking the x derivative of the x derivative, this is where we were. When we find ourselves wanting to take the x derivative of zy, well, the thing we're taking a derivative of is there. The thing we're taking the derivative with respect to is here. And notice the diagram explains it to me. I just have to apply the chain rule. That's how you take the derivative of zy with respect to x. It's another chain rule problem inside of your existing chain rule problem. So that's the big idea. Now, if you carry this through, and the details of how this ends up are not the point. So if you wanted to write a second derivative chain rule for single variable derivatives, this would be it. I do not encourage you to memorize this rule or try to use this result in any way. The point is not the result. The point is that we have thought through how to make sense out of this by thinking through what's a function of what. Okay, and that's an idea that we want to now extend in a multivariable context. And this comes up pretty naturally. Suppose you have a function of two variables. So z is a function of x and y. This is a very, very tame situation, right? Nothing particularly remarkable about that. And then remember, we also have, polar coordinates that give x and y as functions of r and theta. And suppose very plausibly you say, well, I'd like to reinterpret z as being a function of r and theta, and in so doing, how would I take derivative of z with respect to r and theta? That's a pretty reasonable thing to want to do. Well, you've clearly got a chain rule problem here. Right? We've got a composition of two multivariable functions. Right? The first derivative, real easy to write down. Using the chain, let's do the partial of z with respect to r. Right? There are two paths through which changes can propagate. This gives us two terms. So I'm not using the matrix form of the chain rule here. I could, right? But I'm using the intermediate variables, propagation through paths, however you want to think about it, point of view on the chain rule. Two paths, two terms. Two intermediate variables, two terms. Right? So here's our first derivative with respect to r. Okay. Notation. Don't forget, we can rewrite partial of z with respect to x as zx. Likewise, zy. Don't forget, furthermore, x is a known, given function of r and theta. So that's easy to do. Okay. All right. So we've done our first derivative. It's gotten us down to this. And now let's take our second derivative. Right? Let's find the second derivative with respect to r. So we're going to, likewise, by the way, here's the theta derivative. If you want to do that, it's analogous, highly analogous. But let's take now an r partial of the existing r partial see what we get. And the start of that process, R partial of the R partial is, well, there it is, the R partial of the R partial. And we write out our product rule twice. That product gives us these two terms. This product gives us these two terms. Nothing weird has happened yet. But we find ourselves in this situation again where I need to take a partial of zx with respect to r, and can you do that? Is that a thing? And no, it's not. That's not. You can't say this is a function of those, or more likely, this is a function of those, because those are not independent variables. You just can't do that. It doesn't make any sense. Right? So we have to understand this partial derivative by understanding where are the items in question. What am I actually taking a derivative of? Well, zx is there. It's a function of x and y, just like z was. Taking a derivative with respect to r, there's r. And you can see here, just by looking at how these variables, I'm going to call them, appear in our diagram, you can see explicitly that there is a composition. By having it on your diagram, you can see explicitly what are the intermediate variables, what are the paths through which changes can propagate, however you want to say it. And so we get two terms for that derivative. I wanted to switch to the highlighter. There's through the x variable, I'm going to have to zoom out. Through the x variable gives you that term. We're looking at this product rule thing there. Chain rule thing here, excuse me. There's the x term, and then there's the y term. So the chain rule is used again inside of our second use of the chain rule. Everybody on board? If you just follow this pattern, always think about what's a function of what. Append your diagram. Use your the diagram tells all. The diagram is your friend, right? So be careful in constructing your diagram. Be diligent in referring to and following your diagram, and just slowly and carefully, and all these derivatives work out just fine. Analogously, by the way, let's see here. This is another chain rule problem. Again, you get two terms, and those are those. Everybody on board? Okay. All right. So there's a bunch of different variations of these kinds of ideas. If you take derivatives with respect to theta instead of r, the algebra is different, but the strategy is the same. Just make sure to realize what's a function of what, and document, follow the pattern, and go slowly and carefully, and don't assume too much and try to do too much in your head. Okay. All right. So moving along, I'm going to talk about implicit differentiation. Y'all have seen implicit differentiation before, I presume. It's a standard topic in Calc 1 classes, or sometimes Calc 2, it depends. But so the idea is if you want to find a slope, a slope of a tangent line. Slope of a tangent line suggests derivative, but what if you don't have the function explicitly given, and you still want to find its derivative? Right, so we do something called implicit differentiation, and you all have seen how this works in practice. It is usually treated in single variable calculus classes in a very sloppy way for a combination of reasons. One of which is a better treatment, and it's still not a perfect treatment, by the way. There's a lot of rigor I'm going to leave out in this discussion. It's not appropriate for Math 212. But a better discussion would require multivariable calculus, which students in Calc 1 classes have not seen, and it wouldn't be reasonable. Okay. So anyway, let's try to give a more careful and proper treatment. I'm going to try to find the slope of the tangent line to this curve. That curve, of course, is given by the equation x squared plus y squared is, okay, this is a circle of radius 5. So x squared plus y squared is 25. We want to look at the point 3 comma 4. And let's find the slope of that tangent line. So we want to find the function whose graph is this curve, because its derivatives compute slopes of graphs. So we need a graph. We need this to be a graph. Bad news, it's not a graph. Right, so that's right off the bat. Seems hopeless, because look, we failed the vertical line test, and so that's a problem. The solution there is to say, look, if I want the tangent line to this curve, that's the same as the tangent line to that curve. Let's just erase most of that circle. Right? This curve, this purple curve, is a graph. It passes the vertical line test. Right? At the point 3, 4, and by the way, big asterisk. I'm going to come back and talk about that in a minute. So, that being a graph, I can reason as follows. I can say this purple curve here, on that purple curve, y, which, by the way, in the existing algebra, the original algebra that I was given, on this original equation, x squared plus y squared equals 25, in this original algebra, y is not a known function. Y is a input variable in the original algebra, right? But I'm going to reinterpret, in this context over here, I'm going to reinterpret that y is a function of x. Again, that is not suggested by the original algebra at all. But I'm going to interpret that y is a function of x so that if I, by hook or by crook, can eventually do this, I can say, okay, well then the derivative of that y function is the slope of the tangent line that I'm interested in. Okay, all right, so new function. I got to emphasize. Okay. All right, and then we proceed algebraically as follows. We say, okay, well, here's our original algebra. X squared plus y squared is 25, but now wait a second. Y is a function of x. So there's kind of a weird thing going on here. I have a big function of x and y, but y itself is a function of x, and so there's kind of a chain rule situation going on here. I have a composition of two functions, right? X determines y determines x squared plus y squared. So altogether, though, in the composition, this is now a function of x. I've got a great big function of x. It's kind of an illusion. Part of what is a function of x looks like y, but that now is a function of x. And having done so, I can say, let's take a derivative with respect to x. And by the way, this is not a partial derivative. That's a good old, plain old Calc 1 derivative, because this is a great big function of x. Okay. In so doing, okay, well, the derivative of x squared is 2x. The derivative of all of this, chain rule. I'm looking at the square of y, but y is a function of x. And if you apply the chain rule there, its derivative is that. A lot of students will forget the y prime over here. A lot of students just say, oh yeah, the derivative of y squared, that's 2y. Just, too fast and loose there. We're taking the derivative with respect to x of y squared. Chain rule, composition. Don't forget that extra factor. Okay. And having done this, now of course y prime is what we're wanting. We're looking for the derivative of the function whose graph we're looking at, because derivatives of, slopes of tangent lines are derivatives of the function whose graph you're looking at. Okay, I said that awkwardly. Anyway, y'all know what I'm talking about. So solve for that y prime. Just algebraically solve for it, and there's your formula, and it's all downhill from there. Okay, now in practice, what people actually write in single variable calculus classes is much more compact. Students will just very kind of quickly just go straight to there, right? And I'm going to complain about that in a minute. But having done that, then again, you solve for y prime and plug in the point that you're interested in at the point we're interested in. X is 3, y is 4, and there's your answer. Okay, now let me complain. This gets back to the asterisk that I asserted earlier. I just asserted here at this point that if I restrict to that part of the curve near the point 3, 4, I just asserted that passes the vertical line test. I mean, just, erase enough of the curve. Erase however much of the curve is necessary until it passes the vertical line test. Why can't we just do that? Now, in this case, we can because this is an easy problem. We know a lot about circles. Y'all have tremendous experience with circles. And we know that at this point 3, 4, yes, that's true. That's just geometric knowledge. Right? But in general, how do you know that you can do that? How do you know that that you can erase enough of the curve so that the resulting short little bit actually is a graph? And I'll point out that for your consideration on this question, it's not always true. Here's a pretty easy counterexample on the same circle, no less. Let's look at that point, 5, 0. And I don't care how much of that curve you erase, right? However much of this you just say, okay, no, we're going to throw all that away. However much of that you erase, as long as there's a little bit kind of on either side, you need a little bit on either side in order to be able to talk about a tangent line. Right? If there's a little bit on either side, then you're still going to fail the vertical line test. No matter how much you erase. That's a problem. Okay, so the reason that's a problem is because what that means is that at this point, in no sense can you claim that y is a function of x. Not globally in that curve, not even locally on that curve. In no way, no how is y a function of x. And problem, if y is not a function of x, then you sure can't take a derivative of it. That becomes total garbage. Nonsense. You might as well try to take a derivative of a bicycle. It's not a thing. Right? So how are we going to deal with that problem? And this is what single variable calculus classes can't realistically talk about. So there's a way to deal with this, and here's my argument. Here's a couple of different cases of scenarios we might be interested in. Notice we're off of the circle. Let's not presume we have geometric knowledge of what our curve looks like. So here's a curve, and on the one hand, at this point, it's not locally a function, no matter how much you try. Whereas at this point, it is. If you erase enough of the curve, now you got to erase enough of the curve. If you're careless and you do like that, well, now it fails the vertical line test. But that's just oops, right? If you erase enough of the curve, that is locally a y is a function of x. So here's the idea, and again, I'm not going to be rigorous about this. This is not appropriate for Math 212, but I argue, I think pretty plausibly, that the thing that makes this point fail is that, forgive my sloppiness, the curve is in the process of wrapping under itself, or depending on which way you want to feel that you're going, maybe over itself. But it's the wrapping under. That's the problem. That wrapping under is happening at exactly that instant. Why is the wrapping happening? What makes it possible for the curve to wrap under itself at that instant? Well, it's the fact that there's a vertical tangent line. Now, don't forget, this curve here, described by some equations. Equations can all be written as level sets. Right? So interpret your curve as a level set. We know a bunch of information about level sets. And that being as it is a level set, having a vertical tangent line to that level set would mean that we have a horizontal gradient of that function. right? So the gradient, this function whose level set I'm looking at, its gradient has to be horizontal if we're going to have a problem. And by the way, what is the gradient? Now let's write that down. The gradient is partial of f with respect to x, partial of f with respect to y. If this gradient is horizontal, horizontal would mean that there's no second component. In other words, that this second component of the gradient vector is 0. In other words, if we're going to have a problem, let me write this down. Problem would have to imply that the partial of f with respect to y is 0. And now this arrow is going the wrong way. We need to know an algebraic test that lets us know when there's a problem, when there's not a problem. That would be our ideal. So I'm going to write down what we call the contrapositive. Right? So the contrapositive of P implies Q is not Q implies not P. And it's logically equivalent. And so if the partial of f with respect to y is not 0, that means no problem. And this is a sloppy statement, but this is the implicit function theorem as it applies to this circumstance. So this is how we do. This is a more careful way to approach implicit differentiation. If you want to view a certain variable y as being a function of x, or what other variables are in your equation, if you want to view y as being a function, take the partial derivative of the capital F, the thing whose level set you're looking at. Take its partial derivative with respect to y, that same variable that you want to view as being a function. Confirm that it's not 0. And then go ahead. Implicit differentiate all you want. It's fine. Everybody on board? That's the process. This is why it's true. So here's what I would like to see on a Math 212 exam. If you are asked to find the slope of the tangent line to a certain curve at a particular point, and where the curve is described by an equation, which, by the way, is a level set of a specific function f. Right, if you find yourself with this scenario, you can't just jump straight to here. If you jump straight to here, you're making this wild assumption that y is, of course, obviously a function of x locally. That is not at all clear. Right? You've got to establish that y is actually a function of x first before you can actually take a derivative. So here's how we do that. I want to view y as being, if we're looking for slope. Slope means I want to find dy dx. That means I want to take a derivative of y. That means I want to view y as being a function. So I take a partial derivative with respect to y. Compute that out. Confirm that it's not 0. What it is doesn't really matter. All that matters is that it's not 0. Right? Having confirmed that it's not 0, I can treat y as being a function of x. And then, again, all your old Calc 1 calculation, totally fine. Just do the usual down there. Everybody on board? Okay, now just for your reference, just sort of perspective on how much does this matter in a Math 212 class? All of this down here is Calc 1, right? So if I ask you a question like this is not really what I'm interested in. I'm interested in the extent to which what this question is pertains to multivariable calculus. What I'm interested in is that you take the derivative of the correct thing with respect to the correct variable, that you visibly observe that it is not 0. Right? You have to note that. You can't just say equals 8 and then proceed. You got to spike that particular football. That is not 0, obvious though that point is. You got to say it, right? And then you have to explicitly draw the correct conclusion from that means y is a function of x. That's the big stuff that I'm looking for. So at least half of the points of the problem are going to be above that line. And then at most half the points will be the stuff that's below. Okay, is everybody following the argument there? Okay. So now let's take it a step further. What about in a multivariable context? What if I have more than two variables? And by the way, 2, of course, is still multiple, but the resulting function up here, right, is a single variable function. So this is kind of a single variable version, if you will, because again, the resulting function is single variable. It starts off as multivariable, whatever. But in a no kidding, absolutely 100% multivariable setting, if I have some equation like this, with a bunch of variables in it, and if I want to, for whatever reason, if I want to compute a partial derivative of one of them, maybe I want to compute the partial of y with respect to x3, maybe. Right? Whichever one you want to take a derivative of, that's the one that you have to view as being a function. Whichever one you want to be a function, that's the one that you have to take the partial derivative with respect to. And that's our implicit function theorem. I'm going to draw a picture in a setting, but here's the theorem. At a certain point on that level set, take the partial derivative of the function. The function whose level set you're looking at. Take the partial derivative with respect to the variable that you want to view as being a function of the other variables. Right? Confirm that you don't get 0, and then proceed. Take all the implicit derivatives that you want. Before we do an example, I want to look at the picture that I have down here. By the way, this picture is it's not in the book. This is sort of supplemental. I drew this before class started. So here's a kind of a picture of what's going on. Now, if you look at this this surface, this blue surface, it's a level set of some function capital F. And notice, I cannot assert at this point, at this point right there, I simply cannot say that z is a function of x and y. It isn't. That's where the surface is kind of wrapping under itself. At that point, no matter how much of the surface you throw away, it's going to fail the vertical line test. At that point, locally, z is in no sense a function of x and y, and you can't take derivatives of things that aren't functions. Right? So that's the kind of problem that we're interested in. Notice the problem that we're worried about happening is simultaneous with there being a vertical tangent plane to that level set. If there's a vertical tangent plane, then that means that there is a horizontal gradient vector, and that being horizontal would mean that the partial of f with respect to z is 0. So the variable that you want to view as being a function, notice we need to take the partial with respect to that variable. Okay. All right. Okay. So here's an example. Let's look at this equation here, and let's take a moment to recognize that that's a hard equation. It's got 6 powers in it, for crying out loud, right? That's tough, right? Now, I could solve for z locally. I can write an equation that solves for z locally. I'm not going to do that because the purpose of this example is not to get an answer. The purpose of this example is to show how to use implicit differentiation, and I don't want us to get bogged down in algebraic inconvenience. So I've chosen an example where the algebra is nice, relatively nice, right? And let's still use implicit differentiation, even though technically we could find a smart alecky way to skirt the method. Okay. So here's a point on that level set. The question says, let's find the slope of the tangent line to the cross section of the surface perpendicular to the y-axis. Quick drawing. If you want to take a cross-section perpendicular to the y-axis. That's the y-axis. And if you're looking for the slope of the cross-section of the original surface, whatever that surface is, slope of the cross-section in that plane, notice you are taking a derivative in the x direction. Right? So what I'm looking for here is the partial derivative of z with respect to x. So another common mistake is students will very often students will see, oh, it says y right there, so I guess I'll take a partial with respect to y. Don't oversimplify. You got to think through the geometry of the problem. We want a partial derivative with respect to x. Okay, so ideally we would like to compute partial of z with respect to x, but again, in this equation, how do I know that z is locally a function of x and a function of x and y, and then I can take a partial derivative? Okay, how do I know z is a function? And the way we know that z is a function, the thing that I want to view as being a function, I need to take a partial with respect to that variable. Specifically, I'm taking a partial of the function whose level set I'm looking at. Just like in just like in the single variable example that we did previously. Right? So that's the partial derivative I need to compute. It's an easy partial derivative. Turns out to be 6 at the point in question. That's not 0. Therefore, z is a function of x and y. And now, go ahead, view z as being a function, knock yourself out, take all the partial derivatives you want to, viewing z as a function of x and y. Okay, now that's the first half of the problem. There is some remainder to go, but everybody comfortable with the first half of what we're taking the partial of, what we're taking the partial with respect to? Okay. All right, so now we've got to be a little bit more careful. In a Calc 1 setting, there's only one independent variable remaining. Not so here. In looking at this algebra, again, we're just going to implicitly differentiate, but keep in mind the different roles the variables are playing. We've already decided that in this algebra, we went to a bunch of trouble to conclude that z is a function. Okay. But now furthermore, notice, I'm taking a partial of z with respect to x. Well, partial means that I want to view only x as being a variable. So yeah, x is a variable because I'm taking a partial with respect to it, but because it's a partial derivative, that means that y is to be viewed as a constant. Right? The fact that it's a partial means x is the only remaining variable, that we treat y as a constant, and then go ahead. So this is another twist. This is another thing that makes multivariable implicit differentiation a little weirder than single variables. Now look at this. All three of the variables are playing different roles. And you've got to understand, I got to identify correctly what roles are being played by each of the three variables before you go ahead. Now with this in mind, the algebra is no big deal. So we're taking an x partial here. The x partial of the x partial of x squared. X is the variable we're taking the derivative with respect to. 2x. No problem. Okay. Y to the fourth. Stylus. Y to the fourth. Well, now keep in mind, y is a constant. So the x partial of that great big constant is 0. It's not a chain rule problem. It's 0. And then lastly, this z to the 6th. Well, z is a function of x and y. So I have here a function of the 6th power of z of x and y. So that's a chain rule problem. And so we use the chain rule to write down. There's only one intermediate variable, and that's z. Right? So we write, but we do have to do the chain rule there in writing down the derivative of that third term. And now everything's all over but the shouting. Notice that the partial derivative that we are looking for has showed up. So you solve for it and plug in the appropriate point, and there's your answer. So, yeah. Everybody good? A little tricky. Okay, so we are we're going to say momentarily done with Chapter 4. If you paid careful attention to the schedule, you'll notice that we're going to leap over the next 3 sections of Chapter 4 temporarily. We'll come back to them at the end of the course. Very briefly, let me tell you why that is. As y'all have, I'm sure, noticed at this point, this class is packed with content. It's crazy fast. Right? There's so much material that we're covering. And the awkward thing about it is that the most challenging material is actually at the very end of the course. And so the sort of classical story that used to happen in Math 212 is that the most challenging topics of the course would get presented like on the last couple of days of class, and then final exam. Right? It just happens so fast, and students don't have the time to digest. Right? So my solution, and I'm not the only one who does this, but what I like to do is any material in this course that is not kind of prerequisite to that ending material, anything that's sort of an offshoot that we can do later, and it doesn't sort of handicap us in being able to get to that last material. Let's procrastinate it. Let's put it off to the very end. So these next 3 sections of Chapter 4 are that. It's optimization. It's very important material, but it's not needed at all to understand what in this book is Chapter 6, the really sort of challenging stuff at the end. So I want to get Chapter 6 done as soon as possible. I'd do it on the first day of class if I could. But I can't, because you can't do vector calculus without integration. You can't do integration without the setup of vectors and stuff. And you could argue about whether you can do derivatives before integrals, but you certainly need both of those to be able to do the vector calculus. So optimization we can delay, and so we will. So I'm going to move on now to quite a few pages ahead. Let's see if you're following along in your books. This is going to be page 227. We're going to jump up and talk about integrals. Very first thing you'll notice, there's a bunch of stuff written up here that again is not actually physically in the book. This is more supplemental stuff that I added after the fact. So proceeding. Okay, so as I've done several times before, let me talk a little bit about single variable calculus, not because I don't think y'all know single variable calculus, although there's probably a few subtleties here and there that you might be a little shaky on. But because I want to set up a context, right? I want to be able to do multivariable integrals, and the way I'm going to do multivariable integrals is by taking the right point of view on single variable integrals. I got to make sure that we're looking at single variable integrals the right way, the way that's going to make the analogy extend. So the thing that the point of view we're going to need to take here is actually that of the definition of an integral. This is something that is surprisingly poorly understood among Calc 1 and 2 students. It's just, I don't know, it seems to be, it's probably mostly your teacher's fault. Anyway, very importantly, integrals are Riemann sums. And this is not, you could take the point of view that, mathematicians like to be mathematician weirdos, and this is just, if you want to get all abstruse about it, then maybe, I suppose, technically, right? But a lot of students like to think of, integrals are area. This is the way to think about integrals. I'm going to put a question mark next to that, because that's not a good idea. Let's think of integrals as being areas, and I don't know, makes life easier. Let's just do that. Another large collection of students likes to say, nah, come on, integrals, look, that's what an integral is. Every integral that I have ever computed, practically, I've computed with that formula. Come on, that's what integrals are. Well, wait a minute. First of all, which is it? Right? One of them's got to be the definition of what an integral is. Right? Okay. Now, these are both bad. And the reason why is because of the very great number of applications. I deliberately made this circle too big to fit on the page, right? But there's a tremendous number of applications of integrals and the fundamental theorem of calculus. And the way those applications work, practically all of them, is that you take the application, and step one is you write the answer as a Riemann sum. And that being the definition of an integral, you can then use the fundamental theorem of calculus that computes integrals to evaluate it and get your numerical answer. Okay, so this is why Riemann sums are important. They are the connection between what I'm going to loosely call calculus and applications. Now notice I'm not making observations about rigor and abstractions and mathematical aesthetics. Right? This should be the language that most of the students in this, most of y'all aren't math majors, right? By the way, reminder, if you're a math major, if you're thinking about a math major, you should definitely come talk to me at some point. Sorry, side. But most of y'all are not math majors. Most of y'all are going to be interested in doing applications. So this is an appeal to applications. If you want to apply the idea of an integral, you write, for example, y'all have all seen this particular application. You want to take the mass of a one-dimensional rod of non-constant density, along the x-axis or something, and you want to compute the total mass even though the density varies. How would you go about doing that? Well, you write it as a Riemann sum. For example, here is such a rod. Right, along the x-axis. And you say, all right, well, that's A, and this is B. And I'm going to chop that rod up into a bunch of little pieces. On each piece, I can talk about how big is that piece, delta x. We have formulas, right? Then I can say, well, look, if I know the density is a function of position, then on this little piece, on that one little piece of the rod, mass per unit length times the length, that product gives me the mass in that one little piece. So f of xi times delta x gives me a little piece of mass, and then I add up over the whole rod. And notice that's this Riemann sum, f of xi times delta x, and then you add up over the whole rod. You take a limit to make the round off errors go away. Okay, so the way we compute the mass of a rod here is through a Riemann sum. Now I'd like to point out what is conspicuously absent in that argument. My argument that this physics problem can be computed with an integral made absolutely no reference to area. Right? So can you imagine what kind of trouble would you be in, right? If your definition of integral is area under some curve, area under the curve, or whatever curve you're looking at. I don't have a curve. I don't have an area. And if I did, if I were to just make the appeal, well, think of that function, draw its graph, and then compute that area. And then my natural next question is, what's that got to do with mass? Right? Everybody see the problem here? The question of mass simply does not directly connect to the area. This connection here is not clear. So that makes that a bad definition. Okay. All right. So enough of that. By the way, I have gone on at length in a recording on my YouTube channel about this topic. So if you want to hear more of me ranting about how important this is, you can watch that video. But the big point I want to get to is all of these applications. They are addressable by calculus because we've been clever enough to define integrals as Riemann sums, and Riemann sums being the definition of an integral, you can then compute with the fundamental theorem. Okay, so when we say we would like to define a multivariable integral, what we are looking to do in defining a multivariable integral is to define a multivariable version of that. And the applications, I mean, we'll fingers crossed, hope the applications will come. But that's the concept that we want to generalize. Riemann sums. So, this thing. Okay. Alrighty. I want to lay out sort of the structure of a Riemann sum, just again for the purposes of generalizing. And there's some details on here, but the big points here: the domain can be broken up into smaller pieces. Now that's the very first thing we did to our, looking at the mass of a rod. We chop it up into little pieces. You can break up that domain into little pieces, but more specifically, the thing we're interested in computing is the sum over the smaller pieces. So the quantity that we are computing in this strategy accumulates. I like to say it accumulates over that domain. Now you might say, yeah, well, of course it does. Let me point out that no, this is not an of course. Not every object that you want to compute in the real world has this feature of accumulation. So, for example, this rod, if I wanted to compute the center of mass, maybe here, is not the sum of, the center of mass of that piece plus the center of mass of that piece plus the center of mass of that. I mean, it's just not, right? Those centers of mass, if you add up all of these centers of mass, you get some point way over there. Okay, so there are a lot of objects of physical interest that simply do not have this feature of accumulation. And this feature of accumulation is essential if we're going to address that application with a Riemann sum. So I just wanted to note that for the record. That's something we're going to have to be on the lookout for. Here's the second thing that we have, and again, there's some formalities you need to, that's a detail. Second big point, the thing that you're computing on the smaller pieces needs to have a particular algebraic structure. It needs to be a product. It needs to be size times some function. So specifically, on each smaller piece, the quantity in question has to be proportional to the size, and then there has to be, the other factor in the product has to be some function that you can identify. Now, in our example, is mass, this accumulating quantity called mass, is mass a product of size times something? Yes, it is. There it is. It's size times density. It's kind of the definition of density, I guess, right? But anyway, the point is, it has that structure. Function times size. The reason we need that structure is because there it is. Function times size. That's part of the construction of a Riemann sum. Okay, so now I'm just going to, let's talk about how to make the generalization. How are we going to extend this to a multivariable context? And the way you extend an idea is to say, okay, what are the key features of the idea as opposed to what's kind of incidental to the context, and then change the things that are incidental to the context and keep the key features. The key features are the features of accumulation and the connection to size. Okay. All right. So now there's some exercises in here. These are mostly Calc 1 problems. I just want to make sure that everybody's reasonably competent with Riemann sums from Calc 1, Calc 2, depending on your class. So anyway, those should be all review questions. Okay. Now we're going to go on to double integrals. I could just go straight to and write down the definition of a double integral, but I'd rather not just go straight to this. I'd rather motivate this formula for something I'm going to call a double integral. I could motivate it in a lot of different ways. I could go back and I could take any one of these applications here and I could say, hey, let's consider a multivariable version of this, or let's consider a multivariable version of that, and try to deal with it and then have, whatever comes out be our new construction of a Riemann sum. So that's kind of what I'm going to do. And the only thing is the application I'm going to use, I'm going to take a multivariable version of this one, despite the fact that I just got through trashing that, right? It's not that, I want to clarify my trashing. I'm not saying that that's not a good application of integrals. I'm saying it's not a good definition of integrals, right? It's a perfectly fine application. And, if you want to if you want your intuition about integrals to maybe sometimes come from that point of view, I guess sometimes that's okay. Don't hang your hat on it for reasons that we'll develop later. But as an application, it's a perfectly fine application. In fact, it's a really nice application because it's geometrically satisfying. Right? So I'm going to take the multivariable version of this question and use that as our first application, and that's going to derive our multivariable. That's going to motivate our multivariable Riemann sum. Okay, so here it is. Here's the multivariable version of area under the graph of a function of x. The multivariable version would be to look at the graph of a function of two variables like x and y and look for the volume under that graph. Yeah, everybody on board? Okay, so it's a, geometry problem. How do you find the volume under a surface, specifically a surface that is a graph? And there's different ways you can approach this. I'm going to try to take the approach that, again, is most useful for our purposes right now. And remember, we have these points of view here. I would like to be able to think of there being a domain and that the quantity accumulates over the domain. So how can I think of volume as accumulating over little pieces of this domain? And I hope the following picture seems pretty plausible, but I would do it like this. Here's our domain. I can chop up my domain into little pieces. You got to chop two different directions. It's you're not just slicing, you're slicing and dicing. I'm not sure if I'm using those cooking terms correctly, but you slice it one way and slice it the other way. Right? And I appeal to your geometric intuition. The total volume that I'm interested in here, this grand total, all of that volume, is the sum of the volumes of these little French fries that you get by looking at the volume that's specifically over each little individual piece of the domain that we just chopped it up into. What do you think? Geometrically, is that pretty plausible? Yeah. Okay. So we have a picture that looks kind of like that, and now the next rule, the next pattern that we want to confirm continues, is I want to know that on that smaller piece, on that French fry, I would like to know that the quantity I'm computing, okay, now volume, is it true that volume is a product of the size of the piece times the value of some function? And yeah, sure. Right, this little piece, do I have a picture? I guess I don't. But on this little piece, the amount of volume in here that volume is equal to this area down here. Area is the size of that piece. Times, and it'll see the value of some function. What's function? Well, I need to multiply by height. Right? Geometry appeal. Volume is equal to base times height. That height is z we're looking at the graph of f, so that means that z is f. And so sure enough, as required, this thing that I'm trying to compute, this volume is a product of the size of the piece, namely area, times the value of some function, namely the function whose graph I'm looking at. How are we doing? Everybody happy? So now, is this a single variable integral? Oh my gosh, no. This is very different. The domain is an area, right? This is not an interval on the x-axis anymore. So we're in a totally different territory, but the pattern is strong. We have the quantity in question is an accumulating quantity over slicing up the domain into pieces, and on each piece, it's a product that relates to size, just like in a single variable interval. Okay, so now there's a bunch of details to write down. Bunch of details. I hope you all remember in, again, Calc 1 or 2, depending on your course, this whole breakdown. If you're looking at the x-axis, right, and you have an interval from A to B, then we break that interval up into pieces. We call these points x0, x1, x2, etc. And we have certain formulas that all of this gets written down in a single variable calculus class. But this width, delta x, is b minus a over n. Everybody remember that? The formula for what I'm going to call xi here. So that right endpoint of the ith subinterval as a plus I delta x. So I hope everybody remembers that formula and the reason, why is it? I mean, you got to think it through and just look at the geometry of the situation. Persuade yourself that this is right. If you're unclear on any of this stuff, if you're shaky on Riemann sums, you definitely want to solidify that. This would be something you can come talk to me about in office hours, or you can just find an old book, your old calculus book, and make sure to solidify that up. Okay. All right, so we now need to do something kind of like that. In order to, if we're going to say integrals are defined as Riemann sums, well, we have to say exactly what do we mean by the Riemann sum. So same story here now. Here's a rectangular domain, and I've chopped it up into little pieces. Is that going to, no, okay. Chopped it up into little pieces. Here's the thing. The rectangle, I can characterize the rectangle by what are the endpoints of its shadow on the x-axis, and what are the endpoints of its shadow on the y-axis. Okay, just for notation, just so you know, this domain D, I'll do it in orange. This domain D, the notation that we'll use for this is square brackets A comma B, and then we say cross square brackets C comma D. The idea of this notation is that we're indicating here its shadow on the x-axis is that interval, and its shadow on the y-axis is that interval. And the little cross in between, it's not a cross product. It's not like a vector cross product. Right? That cross is just saying that what we're interested in is the whole thing whose shadows are those intervals. Okay, so that's notation that gets used. Heads up. Okay. Okay. So how do I describe a sub-rectangle? Well, here's the thing. In the process of slicing, notice every time you take a slice vertically of the rectangle, you are in effect also making a slice on the x-axis. And every time you make a slice horizontally, you're also effectively making a slice on the y-axis. Right, so slicing up the rectangle, slicing up our domain, well, really all I need to do is I need to slice up, bad color choice, I need to slice up the interval from A to B, And then I need to slice up the interval from C to D. And I observe that these are morally equivalent questions. One has characters A and B. The other has characters C and D. But they're morally equivalent. It's the same. Chop it up into equal sizes. Look at the size. Greater endpoint minus lesser endpoint. Divide by however many slices you make. It's the same argument, right? So that gives us the following details. On the x-axis, here's those familiar equations. Delta x is b minus a over n. Xi is a plus I delta x. And then we look at the individual intervals from one of those to the next. On the y-axis, well, it's morally equivalent. Now, delta y is d minus c over n. It's the same strategy, right? So other details analogous as well. Okay, so again, these subintervals on the x-axis and on the y-axis those are the corresponding shadows of the sub-rectangles in the actual solid, right? So if I come up here and I look at one of these individual pieces, I can describe that individual piece by simply knowing, well, what do its shadows look like down here and over here. A bunch of details. It's got to get said. That said, it's pretty much all over at this point. There's a couple of details we need to think through. But remember, the strategy of an integral was we're going to add up over all the pieces a bunch of individual terms. The terms are going to be some function times the size of the pieces. And now we just have to kind of think through a couple of sort of unavoidable details. I have to add up over all of these pieces. Well, that's got to be not just these, but also those, and also on each, it's got to be pieces that go all over. So it's not enough to say that I goes from 1 to n. I also need to have j go from 1 to n so that I get not just n pieces, but there are actually n squared pieces that I'm slicing this up into. Right? So this is a summation as both I and j both go from 1 to n. So it's a nastier summation. The other little detail we got to talk about is, again, I'm looking at size. Oh my gosh, this is going to take forever to erase. Oh, it's too much. So what is the size of that piece? Well, very importantly, the size is the area. I need the area because area times height is what gives me volume. Volume is what I'm trying to compute. So I need to talk about the area, not the width, not the length. The area of that piece. Well, the area is just width times length. So area, delta x times delta y. And we have ourselves now a brand new kind of Riemann sum. As of the moment, this Riemann sum's only accomplishment is that it helps us compute one application, namely volume under a surface. Again, the point to this calculation is not because we're just so all about being able to compute volumes. Volumes are one application of many. Let's not get too excited about that. The point is we have a Riemann sum that makes sense in a multivariable setting, and we should be highly optimistic that this is going to apply in lots of applications. Yeah, including volume, I suppose, whatever. But again, don't get distracted by that. That was just a foot in the door. This is what we actually care about. Okay. How are we doing? Is everybody happy? Okay. Okay, so this is the thing we're going to be doing stuff with. This then is our definition of a double integral. This Riemann sum that we just motivated is the double integral of the function f. That's the function. That's the sort of the extra factor on the inside there. over our domain. And the domain, where does the domain show up in this expression? Well, the domain is kind of, it's inside of our formula for delta A because it's inside of our formula for delta X and delta Y, which, don't forget, we're made up out of A, B, C, D. That defines our domain. Right? And it's also inside of our formula for xi and our formula for yj. So we don't see the domain and how that's written, but it is highly important in what that expression means. Okay. All right. And our notation to write this double integral, the notation is kind of exactly what you would hope. Notice this, our notation for delta A in this integral shorthand is dA, just like the pattern, just like what we did in single variable calculus classes, right? The function, again, we just kind of recopy there, right? And now in a single variable calculus class, we would have said integral from A to B. Saying subscripts A and B is just a way of telling the reader what is your domain. I'm going to tell you what our domain is here just by a kind of a more convenient little shorthand. I'm going to presume that my domain has a name, and then I'm going to write the name as a subscript, and that's awfully convenient, right? So this notation presumes that somewhere else, somehow else, you know what your domain is for that integral. Okay. All right, so here's our definition. Integrals, double integrals, are Riemann sums. Highly analogous to Calc 1, modified appropriately to the multivariable setting. Yeah.
Why does the sum start at 1, not 0?
Yeah. So there's a bunch of details in here. Let me go back up to here. So it's just an indexing thing, how we choose to define these things. But so looking at here, I've got this interval from A to B, right? And what do I want to call that interval? I'm going to call it the first subinterval. No reason, right? I could call it the 0th. But the problem is, I want there to be a total of n of them. And if I'm going to call, if I have n things, it's kind of aesthetically appealing to label them as 1 through n. That's all. Yeah. Now, you may be concerned, but wait a second, but this starting point is x0, and that's true, it is x0. The nth subinterval has endpoints whose indices are n minus 1 and n, right? So that's where that comes in. Does that make sense?
Yeah. Thank you.
Okay. Yeah, sure. Cool. Okay. All right. Real quick also, another alternative notation. Sometimes this dA, sometimes that gets written as dx dy. You can kind of see where that might come from, because again, it's delta x times delta y, plausible. So you're going to see that also. I will write it that way sometimes myself. Also, and this is a little bit of a subtlety, why did I use 2 integral symbols here, you might ask? There are enough indications on the page already. Looking at what's written here, there's 2 other indications that we're talking about a double integral. For one thing, dA, that says area. That clearly means that we're talking about a 2-dimensional domain. There's no area of an interval. Right? This is clearly a double integral. The domain itself, again, you have to have a clear picture of what that domain is. If your domain is a 2-dimensional thing, well, of course you mean double integral. So the reason I bring this up is mostly just to point out that this is an arbitrary choice. This is done in a lot of books. I'm going to say in application contexts, this is the norm, right? But I want you to be aware, in some other contexts, in more like advanced math classes, it's considered completely unnecessary to have a whole extra integral symbol when this communicates what needs to be communicated. This says, come on, add them all up. Don't make me tell you twice. Right? Add them all up. That's what that says. And of course, you add up over the whole domain, appropriate to whatever domain that is. Of course, I mean, that's just a given, right? So in advanced math books, you're going to see it written with a single integral symbol. So don't assume when you see a single integral symbol outside of Math 212 that means that it's a single variable integral. It is an integral appropriate to whatever the domain is. That's what it is. Yeah. Does that make sense? Everybody on board? Okay. All right. So I'm going to use this notation throughout this book because, again, I think you're mostly application focused in your majors. Okay. And look at that. We're out of time. Okay. Well, we'll go through the examples next time. See y'all later. Have a good day. Oh, and I don't have any homeworks to return. Sorry. Presumably I'll get 2 back tomorrow. See ya.